In this video we're going to cover periodicity, which is the trends across the periodic table. Now we're going to talk about the size of the ions in the atoms in terms of their atomic radius, and we're going to talk about ionization energy predominantly. Now the definition for periodicity is the trends, as I said, or recurring variations in element properties with increasing atomic number. So if we go across the period, the atomic number goes up, and if we go down a group, the atomic number goes up. Okay, so hence we can just say with increasing atomic number. Now the structure of the periodic table is like this, and hopefully you've seen this in a previous video or you've seen this in your lessons. And you can see that the quantum number or the period, okay, tells you the number of shells that you have. So we've got 2 shells here and then we've got 3 shells here. Now our example here is sodium, so if we look at sodium here we can see 1, 2 and 3 shells. Okay. Now that continues down the periodic table, and then we go into group numbers. So if you look, sodium is still in period 3, so 3 shells, and group 1. So group 1 indicates the number of electrons it generally has in its outer shell. So you can see there's 1 electron up here, which is 1 electron in its outer shell. That works for groups 1 through to 7 and then 0. For transition metals, there are other things you have to take into account. Now if you go across, you can see that means there'll be 2 electrons in group 2, then 3 in group 3, 4, 5, 6 and 7. That means I now know all the outer number of electrons in those elements. And then we finish off with group 0, which has a full outer shell, and therefore 8 or 2 electrons if you're in the outer shell, if you're talking about period 1, for example. Now, just worthwhile reminding ourselves that the periodic table is organised according to proton number, and as we just said, in groups they have similar electron arrangements with the same number of outer electrons if you're in a certain group. Now, if you look here, again, done on a previous video, in terms of electron configurations, you can see we have blocks as well in the periodic table. We have the S block, we have the D, and we have the P, and we have our F underneath, all coloured here. Okay, and you should be able to do electron configurations by now of elements within those blocks. Now, talking about a trend. So the first trend we're going to talk about is non-metallic character. So non-metallic character goes up towards where you've got fluorine. Okay, now that means it's going to gain electrons. So that if you're going to have an element that is towards the top right of the periodic table, it's going to more likely gain electrons. And then we do the opposite here. We have metallic character increases as you go down towards francium, which is more likely going to lose electrons. That's our first trend. Now, atomic radius. Now, if we pick a period, and we've got period 3 here, we're going to talk about period 3 quite a lot during this video. And you can see period 3 consists of S block and a P. Okay, so an S block and a P. And I'd recommend you have a periodic table in front of you whilst you're watching this video. Now, if we look at the atomic radius of these elements, first of all, let's look at the number of shells. So as we go across from magnesium to aluminium to silicon, we can see that because they're all in period 3, you can see there are 3 shells. Each time, 3 shells. So we're not increasing the number of shells as we go across the period. If we look at our number of protons, though, we have 11 protons for sodium, then we have 12 protons for magnesium, 13 protons for aluminium, and 14 protons for silicon. So the proton number, or the atomic number, is going up, but the number of shells are staying the same. So the electrons that have been added, you can see this extra electron here, okay, and then an extra electron right here, and then an extra electron right here. So the electrons are being added into the same shell, but the number of protons is going up. Now what that means is because the protons are holding those electrons in place and the number of protons are going up, that means that it squeezes the electron cloud, just contracts it just a tiny, tiny bit. And we can show this here. So as you go across, and these pictures are not to scale, okay, they're just trying to demonstrate that the atom will get smaller. You can see that the radius is getting smaller as you go across. Okay, so as you go across, this radius is getting smaller. And that's because the proton number is going up and because the electrons are entering into the same shell, which means the attraction for the outer electron is going to be slightly higher. Let's talk about this in terms of an exam answer then. So the exam answer is the atomic radius decreases across the period as proton number increases, so it's really important that you say proton number, okay, and that the electrons are entering into the same shell. And that's really important as well. Now, which will become more important later on when we talk about ionisation energy, this means the attraction for the outer electron increases, okay, and that means the outer electron in the outer shell just shrinks that little bit, and you get a smaller atomic radius as you go across the period. Now let's look at going down the group. Okay, so again, we're going to take out a couple of examples here, and you can see this time, if we go from lithium to sodium, you can see that there's an extra shell. So there were two shells, and now there are 3. Now, if we continue this process and we go all the way down, every single time you go down a block in the group, you'll see that you add 1 more shell. So by the time we get to the bottom here, you go 1, 2, 3, 4, 5, 6. Okay, so we have added 6 shells as we go across. Each time we go down, we add a shell. Okay. Now let's have a look at this in terms of a pictorial view. Again, not to scale, but you're seeing that this atom is increasing in size this time because the number of shells is going up every time I go down to the next period. And I go down the group. Okay, you will see that the atom is growing in size, so its atomic radius is increasing. So what you need to say again for the exam is atomic radius increases because the number of shells increase. And that means your attraction for the outer electron decreases. Okay. And we do include this word shielding. And shielding is this repulsion between the electrons that are in the shells. So if you have extra shells, that means you have extra electrons, which means you get a little bit of repulsion and it pushes that shell slightly out. It makes it slightly bigger. And if it makes it slightly bigger, the radius increases. And that also means that there's a weaker nuclear attraction. So that nuclear attraction between the nucleus and the outer electron gets a bit weaker as well. Now, this then leads us on to ionisation energy. So ionisation energy is the energy required to remove 1 electron from each atom in 1 mole of gaseous atoms of an element to produce 1 mole of gaseous positively charged ions. That is a real mouthful, and I'm not surprised that you look at that and go, how am I meant to remember all of this? Well, the important thing is, how I teach it, is to say, look, don't really try and remember the words as such. It's easier to remember this. It's easier to remember, and we've got sodium as an example here, but you could just put X, essentially. You've got sodium. Well, there's the gas. So if we look here, it says energy required to remove 1 electron from each atom in 1 mole of gaseous atoms. Well, there's the gaseous. Okay, and there's the gaseous. And we said to remove 1 electron, there's your 1 electron. Okay, from 1 mole, here's 1 mole of sodium, here's 1 mole of sodium plus. So I encourage people to write out the equations and just get used to the equations, because if you remember the equations, you can work out this definition and you can remember it from there. Now let's look at the trend in first ionisation energy across the period. So we know from our previous slide that as you go across the period, we've got all of them here, that means that the radius is going to get smaller. It's going to decrease. Okay, so as we go across this period, 3 examples that we've got here, we are definitely, as we go across, we're going to get smaller. So as we get smaller, the nuclear charge, then that's because the nuclear charge increases, as in the number of protons increases. Remember, we're going into the same shell. So the electrons are going into the same shell. So the reason this decreases is because the proton number, the nuclear charge as such, is increasing, but the electrons are going into the same shell, so it's decreasing in atomic radius. So we say here decreased atomic radius. That means there is greater nuclear attraction, which is this last bit here, for the outer electrons. Now, ionization energy is removing the outer electrons. So if there is a greater attraction for the outer electrons, that means that the first ionization energy increases across the period. It's going to be much harder to take an electron, off one of these elements towards the right than it is to take it off sodium, because sodium is larger and the nuclear attraction is less. Now let's look at the trend down the group. So we've got group 1 again here, and you can see as we go down the group, using our previous knowledge here, we know that the number of shells is going up. Because the number of shells is going up, the size of the atom is growing. Okay, so the atomic radius is increasing. So because the atomic radius increases, you will get the nuclear charge, the increased nuclear charge. Notice we don't highlight increased nuclear charge because you don't really need it in the questions. Okay, but that is outweighed by the increased shielding. So as you add a shell here, the more shells you have, the more shielding you have, the more slight repulsion you get. And because there's a small slight repulsion, the atom just gets ever so slightly bigger. Okay, and if it's bigger, that outer electron, think of it like this, the outer electron is further away from the nucleus, and therefore the nuclear attraction is less. And there's less attraction for the outer electron, so therefore, as we go down, the first ionization energy decreases as you go down the group. It doesn't take as much energy to remove the outer electron because the electron is further away. And why is it further away? It's because of the shielding. Okay, and it's because the atomic radius is going up. Now we're going to talk about subshell trends in first ionization energy. And we're going to talk about the examples in period 2. So if you look here, we have the first ionization energy on the left of the graph, and then we have the atomic number underneath. These atomic numbers tell you what elements they are. So we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Now, if you look at this graph, there are two major points that we need to focus upon, and that is the beryllium going down to the boron. Boron does not go as low as the lithium, but the beryllium goes down to the boron. It shouldn't really go down because we know that the general trend is the first ionization energy goes up, and you can see the trend line here. It's because the atomic radius decreases because the proton number has gone up, so the nuclear attraction for the outer electron has increased. Okay, but that should mean that the energy needed to remove is going to be more, but it's not, it's less. You can see this trend repeated to nitrogen to oxygen, so oxygen is slightly higher than carbon, but lower than nitrogen. It should go up. Now in the exam, they're very keen that you can answer this type of question, and one or the other can turn up. To answer it, we have to look at electron configurations, and we have to look at orbital diagrams. So let's look at boron first of all and do its orbital diagrams with these boxes representing an orbital. We know with boron there's a 2s orbital and 3 2p orbitals. Now if you look at that, you fill the 2s first, and you know how many electrons you have to fill because boron's in group 3, so therefore 3 electrons in its outer shell. The third electron will go there because orbitals have up to 2 electrons in them, so that's full. So then we move on to the 2p. If we then do this in terms of oxygen, okay, we fill the 2s again, and let's just check how many electrons we need again. Oxygen group 6, so therefore 6 electrons to place. Okay, and that's our third electron. Now the important thing here is you will singly fill these orbitals before you pair them up. So single filled, and we've got 5 electrons, we need to place 6, so there's the 6th. Okay, so these are our 2 electron configurations. Now let's focus on why this means that the ionization energy, first ionization energy goes down. So let's look at boron first. So boron is a p block element. It's a p block element because its highest energy electron is in the p block. That means this is the highest energy electron. Higher amount of energy means you're slightly further away from the nucleus because you have the energy to escape the pull of the nucleus, okay, which means that's slightly farther away, which means it takes less energy to remove it. So essentially, if we put that into an exam answer, why does boron have a lower first ionization energy than beryllium? It's because the electron is lost from a 2p orbital, so we're losing it from this orbital here, Okay, and that orbital has a higher energy than the 2s. And that's how you do it in an exam. Now let's look at oxygen. So oxygen's slightly different example. Remember, we're trying to explain why it goes down a little bit. Now, it goes down because of repulsion. So these two electrons that are here are right next to each other. And remember, from base principles, electrons are negative. So if this is negative, they're right next to each other in the similar space. Okay, they don't like being next to each other, so they repel each other just a little bit, get a little bit further. They get a little bit further, they're a higher energy again, and if something is a higher energy, it's easier to remove, or the electron is higher energy, it's easier to remove. If we put that into an exam answer, okay, why does oxygen have a lower first ionization energy than nitrogen? It's because the 3p paired electrons repel each other, which means it takes less energy to remove the outermost pair electron. Okay, so it takes less energy to remove this one. Okay, and that is how you explain the two trends. Now, I mentioned at the start, this trend goes across period 3 as well as period 2. So you may get asked this, but it's exactly the same graph as you go across period 3. So just remember they're both exactly the same. We're going to do now successive ionization energies. So successive ionization energies are the ionization energies as you remove the next electron from an ion. Now, what does that mean, really? What that means is your first ionization energy just removes one electron, okay, from 1 mole of gaseous atoms to form 1 mole of gaseous positive ions, okay, and that's your first. Your second is just to remove the second electron. So to remove the second electron, you take the already positive ion, and then you remove the second electron. So we're still only removing 1 electron each time. We're not removing them all at the same time. So 1 electron each time. So the third one is to take the 2+ ion, turn it into the 3+, and remove an electron. Now, you're not expected to know definitions of second and thirds, by the way. You may look at the equations within an exam, but not the definitions. And then we got the fourth one, which is 3+ going to 4+ plus an electron. So let's look at the style of questions you're going to get in your examinations. So first of all, this is a ionization energy on the left, okay, and this tells you which ionization energy it is. Okay, so we've got first, second, third, fourth, fifth. And the question you'll get will be, why do the successive ionization energies of magnesium go up? That's your first one. So they go up because, let's just move this to the side, and they will go up because of this, which you've already learned, which is the atomic radius can decrease, but we're doing the atomic radius decreasing for a slightly different reason this time. So as you go from the first ionization energy to the second ionization energy and so on and so forth, as you keep on taking electrons off, that means the charge on the ion increases. So we're going from Mg to Mg plus to Mg2 plus to Mg3 plus. That means if I go across this side, you have 3 excess protons. That means your nuclear charge is going to be higher than your number of electrons. Okay, so your nuclear charge is going to be higher than your number of electrons. There's not balance there. And what that means is that the protons are going to shrink in the electrons, pull them in, because there's more of the protons than there are electrons. And so as the charge of your ion goes up, your ionic radius goes down. Now, if your ionic radius goes down, that is why you can explain this general trend. So the general trend is going up because of the ionic radius going down, okay? So the radius of the ion decreases and the attraction between the remaining electrons, or the electrons, and the nucleus increases. Right. The next question is, why does this provide evidence for shells or energy levels? Now, the important thing here is that you're looking for essentially gaps. Big rises. So if you look here, we can see a big rise. So let's have a look at, you can see with the rest of it, you can see it's fairly steady. Okay, here fairly steady, but then here, big jump. Okay, so it's really important that you can see that. So let's go through the ionisation energies first of all. So you can see I've just highlighted down here, I've highlighted the first ionisation energy. That's removing an electron. So let's look up here and remove that electron. Okay, so that electron is now gone. Okay, that's the first ionisation energy. We'll then go back down here. We're going to highlight the second ionisation energy. Remember, that's removing the next electron. So we're going to take this electron right here, and we're going to get rid of it. Okay, now we're going to go to the third ionisation energy. Now, notice all of the electrons in the outer shell have gone, which means that you are removing an electron from an inner shell. Okay, so let's remove the electron from the inner shell, and that electron there has gone. Okay, so we're going to remove the electron from the inner shell. Now that means that inner shell is closer to the nucleus. If the inner shell is closer to the nucleus, it's going to take more energy to remove it. It's going to have higher nuclear attraction. It's going to be more attracted to the nucleus because it's closer. Okay. Now, if that's the case, it's going to take more energy to remove. And that's why you get a big jump, because you're removing an electron from an inner shell. So that large difference or increase shows the electrons is removed from an inner shell. And then here, again, this is more of an exam technique thing, then tell them where the rise is. Well, the rise in this case is between the second and the third ionisation energies. Okay. Now this means, and this is important for later, this means there is 2 electrons in the outer shell, because, notice, no big rise. So that means first and second I've removed 2 electrons. They must be from the outer shell. Then a big rise. Well, that must mean this is removed from the inner shell, which means I now know from this that whatever element I had is going to be have 2 electrons in the outer shell. This leads on to my next question. Okay, so in my next question we're going to discuss why or how you can identify the element through it. So really important here that you recognise there are 2 electrons in the outer shell, and that means that third is pulled from the inner shell and taken from the inner shell. So let's identify an element. So they can give you a graph like we have given you in the last 2 questions, or they can just give you a table. So here we have a table, and what you have to do with a table, and we're going to give you a little exam tip here, if you get a table or you get data, it doesn't have to be in a table, it can just be lined up, okay, you have to look for the differences in the table. So you have to look for the differences between these numbers. So 2298 minus 1251. You look at the differences, because then you're giving an idea of whether there's a big jump or not between the first and the second. You identify then the large increase in the data. So let's look at that data. So the difference between the numbers we've put here, and you can see that they do vary a little bit here, but they're not hugely different from each other. Okay, they are varying, but not hugely different. But then if you look at the last one, that's massively different. That's 22,000, where the rest are vaguely around the 2,000 area, 2,000 to 3,000 area, whereas this is massive. Okay, so what you then do is you say, right, okay, that means the first, second, third, fourth, fifth, sixth, and seventh ionisation energies, they must have been from an outer shell, and then the 8th one must be from an inner shell. That means that this element has 7 electrons in its outer shell. Now this is in period 3, which means it has 3 shells, okay, which means the outer shell must have 7 electrons in it. So there we have 7 electrons in an outer shell, and then we've just filled in the inner shells. If you then look at period 3, what element this is, it is chlorine. Okay, so we've identified chlorine by using the ionisation energies, or successive ionisation energies. Now, our final question is using ionisation energies to find a formula. So again, common question. The first 4 successive ionisation energies of an element Y from period 3 are shown in kilojoules per mole. We're going to use the same technique that we used before. We're going to look at the differences, but I've just shown you that it can be presented in a different way and not necessarily a table. So what we've done now is just looked at the differences, and you can see the differences here. Okay, and so I can see the difference between the first and the second is 4,000, whereas the difference between the third and the fourth is 2,350 and 2,600-ish. Okay, you can see that this is massively bigger than these two, okay? Now, because that means there's a big jump between the first and the second. Now, the question normally is given as a multiple choice, and it will say, what is the formula of the nitrate? And then here are all of your options, okay? So we need to know that a nitrate is NO3, okay? And we need to then pick out our options. And to do that, we need to know what group this is in. So it's in period 3. What group is it in? Well, the big jump is between the first and the second. That means that the first must have taken it from an outer shell, and then the second must have taken it from an inner shell, which means this element has 1 electron in its outer shell, and it is in period 3. The only one with 1 electron in its outer shell in period 3 is sodium. If you then look at sodium, sodium is a positive ion, NO3 is a negative ion, so your formula will be NaNO3. NaNO3 fits YNO3 as the general formula. So your answer for this one is YNO3.